Let's do this problem from the review in chapter 15, number 31. They want us to find the triple integral over some solid E of y squared times z squared dv, and E is bounded by the paraboloid x is equal to 1 minus y squared minus z squared, and in the plane x is equal to 0. So we're going to need to know something about the shape of this solid, and one way to do this is to try to draw it. And if we try to draw it, we see that this is a paraboloid that is an x is equal to, and then y squared and z squared, those variables are squared. And so this should be a paraboloid that's opening either towards the positive x or the negative x. And since we have two negative signs here, it looks like it'll be opening up towards the negative x, and the intercept is going to be at x is equal to 1. So let's put a 1 here, and then it's going to be opening towards the positive axis. And at the x is equal to 0 plane, that's the yz plane, it looks like it's going to get cut off there, and then we're going to have this paraboloid opening towards the negative z-axis. Okay, what's important here is that we're going to get an image or a shadow on the yz plane that's going to be this circle. So your solid will have this boundary of a circle here on the yz plane. And that means if we're going to do this in cylindrical coordinates or polar coordinates, we're going to have to treat y and z as our x and y. What does that mean? That means instead of using x is equal to r cosine theta and y is equal to r sine theta, we're going to use y is equal to r cosine theta and z is equal to r sine theta. So we're just switching the variables. Instead of looking at this as our old x as our old y, we're going to have this as y and z. Okay, so that's going to be our polar coordinate transformation, which means x is going to remain x. So the transformation is going to be x equals x, y is equal to r cosine theta, and z is equal to r sine theta. Now you could have also set z equal to r cosine theta and y equal to r sine theta. You could have had those switched. But if this wasn't going to be the whole circle, then the angle measurement is going to be really tricky. So I just set the y equal to r cosine theta because I can pretend that's the x-axis, and my angle starts at 0 here, and it goes to 2 pi. So if for some reason this only goes to a quarter of a circle, then I want to make sure that I start at the right place at the positive y-axis. So that is that's our starting point. And now, because of the relationship between y and z and the r cosine theta, r sine theta, we have a y squared plus z squared is equal to r squared. So that's that circle over here that we're looking at on the yz plane. And that will be helpful for us because when we replace your x limits, we can see that x is actually equal to 1 minus y squared minus z squared. Well, that's like 1 minus parentheses y squared plus z squared, which is equal to r squared. So this, in effect, will become 1 minus r squared. And that will end up being our top limit. So when we're ready, and we are, we're going to find our limits for x, and then r, and then theta. So let's deal with the x first. If we draw a line parallel to the x-axis, we will enter through the region via this x is equal to 0 plane. And then we're going to exit the region via the paraboloid. The paraboloid, which we said was going to be 1 minus r squared. Now that we have one variable taken care of, we look at the yz plane and notice that it is just a circle. The radial distance goes from 0 to 1, and the theta goes all the way around from 0 to 2 So our integral is almost set. The only thing we need to worry about is our integrand, and we know that that's just going to be each of these things squared. So let's write down our integral. Oh, one more thing, the dv will have an extra r. So our integral will then be a triple integral. We have y, which is r cosine theta, quantity squared. We have z, which is r sine theta, quantity squared. And now our dv. So our dv is, because we're going into cylindrical coordinates, we'll need that extra r that we've always put for our polar and cylindrical coordinate transformations. And then it looks like we're going to want to integrate with respect to x first, because it's not all constants, and so the order is going to matter. And since x is the only one with a function, we want to integrate with that first. It goes from 0 to 1 minus r squared, and that's our function. And then now it doesn't matter, but we tend to always integrate with respect to r first before theta, and then d theta goes from 0 to 2 pi. All right, we can easily split this up. Um, we have to consider the r, though, very inside at the innermost level, and so uh, this, with respect to x, is constant, so we can take that out. That's not a problem, but we need to integrate with respect to x first. And actually, this is already prepared here for us, and if we do this integral using Wolfram alpha or something like that, we can just go ahead and punch that in and get us solution. And it looks like our solution is going to be pi divided by 96, a very small number. So this is our result, and with the proper integration and putting in limits, that's going to be our answer. Okay, so I hope that helps.